Hi everyone, welcome to Mathemly. Welcome back to our neural networks series. In the last video, we explored the activation functions and saw how nonlinearity gives networks their flexibility. Today, we are zooming in on the fundamental building block of every network, the neuron itself. We will see how a neuron combines inputs, applies weights and a bias, and produces an output that drives the entire learning process. So, let's dive in. Think of a neuron as a tiny decision maker. It receives inputs. These might be pixels from an image, sensor readings, or numbers describing a person's health. Each input is paired with a weight which tells the neuron how important that input is. The neuron multiplies each input by its weight and adds them all together, creating what we call a weighted sum. Mathematically, it looks like this. Z equals W1 times X1 plus W2 times X2 all the way to Wn times Xn plus B. Here, the X's are the inputs, W's are the weights, and B is a special term called the bias. The weighted sum Z captures all the information the neuron has about its inputs, but it is still just a single number. In many ways, a single neuron behaves like a simple linear regression model. Each input contributes proportionally based on its weight, and the bias shifts the output up or down. Let's visualize this using just two inputs. Z equals W1 x1 plus W2 x2 plus B. If both weights are positive, the neuron's output increases as both inputs increase. If one weight is negative, that input pushes the output in the opposite direction. Changing the bias moves the whole prediction curve upward or downward, just like shifting the intercept in a regression line. Each weight acts like a volume knob, turning its input up or down. If a particular feature strongly influences the output, take temperature when predicting ice cream sales, on hotter days sales usually rise. If the network sees this pattern, it will learn a large positive weight for the temperature input, meaning that as temperature increases, the neuron's output and its prediction of higher sales increases as well. If the relationship was reversed, say we were predicting the demand for hot chocolate, the weight for temperature might become negative because higher temperatures would lower the demand. During training, these weights are the main things the network learns. By adjusting them slightly after every example, the network gets better at making correct predictions. Along with weights, each neuron has a bias. You can think of bias as a baseline or an offset. It lets the activation function shift left or right, so the neuron doesn't have to pass exactly through the origin. Imagine you're drawing a straight line to separate two groups of points on a graph. If there were no bias, your line would always have to cross the point 0, 0 or the origin. But data in the real world rarely lines up that neatly. The bias acts like a vertical slider, letting you move the entire line up or down until it best separates the data. This flexibility is crucial. Without a bias, the neuron could only pivot around the origin and might never be able to position its decision boundary correctly. With weights to set the slope and bias to set the offset, the neuron can place that boundary anywhere in the input space to match the data. Now that our neuron has combined its inputs using weights and added a bias, it ends up with a single raw value, the weighted sum. But this raw number alone doesn't tell us much. The neuron still needs a way to decide whether that combined signal is strong enough to activate or stay quiet. And that is exactly where the activation function comes in. Here, we are not introducing new activation types like in the previous video, but rather seeing how activation completes the neuron's decision process. If the total input strongly supports activation, the neuron passes a high signal forward. If it's weak or uncertain, the neuron outputs a small or zero value. This simple step transforms a raw linear combination of inputs into a meaningful output, effectively turning numbers into a decision. It's how a neuron decides, should I pass this signal forward or not, connecting the logic of weights and bias to the behavior of the entire network. Think of a smart thermostat deciding whether to turn on the air conditioner. It looks at inputs like room temperature, sunlight, and time of day. If the room is very hot, the temperature input will have a strong positive weight because it greatly increases the need for cooling. Sunlight might have a smaller positive weight, while time of day could have a negative weight if it is late at night. The bias sets the base comfort level like your preferred default temperature. All these weighted inputs are added together, and once they pass through the activation function, the neuron outputs its decision, cooling on or off. To sum up, a neuron makes its decision by computing a weighted sum of inputs, adding a bias, and then applying an activation function. Weights determine the importance of each input, the bias provides flexibility, and together they form the foundation of learning in every neural network. In the next video, we will see how many of these neurons work together during forward propagation, the process of sending data through the entire network to make its very first prediction. If you found this video helpful, don't forget to like, share, and subscribe to Mathemly for more data science tutorials. Comment below with what you would like to learn next. Thank you for watching and see you next time.